Hello guys, hope you're doing well. My name is Mahmoud Kiosari and welcome to the first chapter of electronics. So at this kind of videos, we are trying to dive down a little bit more inside the electronic part and talk about the thing that actually related to. The very first part that we are going to talk is about why we're talking about electronics, what are specific tools that we need in order to understand them. And later, we are going to talk about the formula and anything related to it. So, without further ado, let's just jump in. So, as you can see over here, at this point, we are going to talk about the atomic side, about the atomic theory, semiconductor fundamentals. The semiconductor is a very important fundamental part of each electronic aspect. So, other objectives that we do have for this course is that we would like to master specific kind of things. The very first thing that we have to see and we have to understand is about the atomic structure and electron orbital behavior. We would see that when we are talking about the electronics, when we are talking about the specific tools that I mentioned, how they actually built by themselves and how actually we are going to use them and based on different kind of sources and different kind of materials that are connected side by side, how actually we can make electronics. Then we have to see it differentiate the physical distinction between conductors, insulators, and semiconductors. If you guys remember from the electrical course, you know that we do have three important type of material: the conductor, insulator, and semiconductor. At this part, we are going to see that how actually we are going to distinguish them, how actually we are going to talk about each of them, and how are we actually going to say that which one is which. Then we are going to explain the valence band concept and its direct relationship to conductivity. This is the very important part because right now we are entering the era that we are going to see that when we are talking about each one of those materials, how we are going to distinguish them or how we are going to divide them into different categories and what is our tool, what is our rule about them. Then we are going to classify, obviously, how materials are going to be categorized based on the valence control, as I just told you. And finally, we are going to analyze the impact of thermal energy or temperature on semiconductor performances because semiconductor is a very important part of electronics. So we'll see about that. So the very first thing that we have to know is the fundamental unit, atomic structure. As you guys know, probably from your physics or chemistry, we do have the atom. And as you can see on the left-hand side, we do have the atom itself. Atom contains three important parts. The very important part that it has two crucial things in itself is something that we call it as a nucleus. So nucleus contains two important portions or two important material. We got it as proton and neutrons. So proton is specific thing or a specific part of the atom that has the positive charges, while neutron doesn't have any specific charges. Then we do have the third important part that we call it as electron. So electrons are going to orbit around the nucleus itself and they're going to have the negative charge. The whole idea, the whole thing of this electron, proton, and neutron is something that we call as electrically neutral system. So again, let's recap this. We do have the atomic components. It means that the atom contains of dense central nucleus, contains positively charged, as we know as protons, and and some kind of neutral neutrons. So it means that at this point, I do have the nucleus and I do have positive and neutral part. All of these guys are surrounding this cores are negative charged electrons that are orbiting in specific energy shells. Well, we'll talk about the energy shells, by the way. But one thing that you have to know is that electrons are orbiting around the nucleus. So the neutrality rule, it says in a stable atom, the number of protons equals the number of electrons. It means that when I do have my nucleus over here, and obviously there are some number of protons and neutrons. By the way, remember that always the number of neutrons and the number of protons and neutrons are the same. So the thing actually that would change at this stage would be about what? It would be about the number of electrons. Specific material, a specific atom either can have some, or either can lose some, or at this point it can be stable, and it means that the number of electrons is the same as the number of protons. So the positive let me just change the color, the positive and negative charges are going to cancel out each other out and are going to have the net charge of 0. So this is something that we know about the stable condition of an atom. So let's talk about the architecture. Let's talk about electron shell capacities. What are they? How we are going to distinguish them? As you guys see over here, you see that there are different type of shell. There are different type of shells that we do have around the nucleus itself. Each of these orbits or each of this path that electrons uses in order to orbit around the nucleus, they do have a specific name, from the closest one to the further one. So what do we have? So at this point, we are going to see that electron shell parameters. We call the first shell or the first order or the first layer as the K. Then we just call the second one as L, the third one as M, and the final one as N. And inside each of these shells, we do have a specific capacity. It doesn't say that we can put as many electrons that we want. No, we do have capacity. The capacity of the first shell or the K shell is 2. The capacity of the L shell is 8. The capacity of M is 18 and N is 32. As you can see over here, K is going to be the lowest. It would start from here. Then we do have L, we do have M, and we do have N. One thing that we have to be careful, or we have to see that actually is happening over here, is that by moving from K to N, we are doing increasing the energy level. What does that mean? It means that if I do have the electron that exists at the furthest some kind of layer, I need more energy to keep that one inside my orbit. If I do have one over here, I need less energy to keep that one in my orbit. Or in total, I can say, we can consider it as a law, that the electrons require more energy to exist in shells further from the nucleus. The further we are from the nucleus itself, the gravity or the energy that the nucleus has for them would be decreased. At this point, I need more energy in order to keep them. Rather than that, by having an external energy or any other kind of environmental factors, that electron could release itself from the whole atom. So let's talk about the valence shell, because we talked about it, that based on the valence shell is the part that we can distinguish different kind of material. So the definition is over here. The valence band is going to be the outermost electron shell of an atom. It means that we are talking about the final layer, which is going to be N at this point. So we do have this band, and then we are going to define it. While inner shells provide structure, the valence shell determine function. As I just told you, based on the function of electrons that we do have over here, based on the numbers, we are going to categorize them. So what is the constraint over here is the maximum of capacity. It means that I only can have what? I only can have 8 electrons at the valence shell. Another thing that I have to mention over here, which could be a little bit confusion, is that based on the last part, you mentioned that the outer layer or the furthest layer, when you compare the distance between itself and nucleus, is considered as N, and it can contains up to 32 electrons. So how come you only have what? How come you only have 8 electrons at this point? So I can say this answer that the valence shell or the valence part, which contains electrons, up to 8 electrons, because this shell is the one that actually is going to have main participation in the connection between the atoms itself. So if you would like to talk about it, it would be a little bit more in advance. So that's why I'm trying to stop it over here, but just have something in your mind. The valence shell is the one that we consider that can have the capacity of only 8 electrons at most. Let's move forward. So as we just mentioned, the valence shell only can the capacity of up to 8 electrons, and the full shell is stable. Right now, as you guys just know, it means that the number of electrons and the number of protons are going to be the same at this consideration. If something happens to that, at that point, material is going to be changed. So its partially filled shell allows for chemical bonding and electron flow. What does that mean? In a normal condition, if you have the full bond, if you have the full number of electrons, everything is so stable and everything is so tight. But if I do have some kind of consideration for myself, for instance, if I don't have that sum of those numbers, it means that right now I do have enough space to accept other kind of electrons from other part of atoms. At this point, I can have connection between the atoms itself and I can use it actually. So let's talk about the critical relationship. There is a direct one-to-one relationship. It means that the number of valence electrons determines the electrical conductivity. And also where an electron sits determines what it can do. As I just mentioned, the number of electrons on the valence shell is very important to us. Why is that? Because it's going to show us that how conductive my specific material is. How I can see that? Let's move to the next page. So at this point, we do have the spectrum of conductivity, the 1-4-8 rule. We use this number is because most of the materials that we are going to consider and how they made up or how they some kind of characteristics, based on their characteristics, we do have these three important number, 1, 4, and 8. So what does one means? What does one mean? Actually, it means that we are dealing with a conductor. A conductor is the one, like copper, silver, gold, better than me. The conductor is a specific kind of material that only have one electron at the outer shell, or at least we know the shell that has the maximum capacity of 8. It means that right now it has 7 some kind of free seats while one is taken. Another part, if you do have it as the semiconductors, it means that I do have the atom, specific kind of atom, that it's in valence shell, it has 4 electrons. So half of seats are empty. So we can call it as semiconductors. Semiconductors are silicon and germanium. Then we do have the insulators. It means that at this point, as we just saw in the last part, everything is stable. It means that all of those 8 electrons are occupied and all of them are set on the last or the valence shell. So we can see as the rubber, glass, and plastic. So as you can see over here, the conductors, they have the exon flow of moving electrons. A semiconductor, they have controlled flow. Either they sometimes they can be considered as insulators. Sometimes they can consider as a conductor is based on how we are going to manage them, how we are going to control them. And finally, we do have the insulator. They're going to have no flow at all. So this kind of material classification is determined strictly by the number of electrons in the valence shell. 1 conductor is loose, 8 is locked completely, so some kind of insulator, and 4 is going to be the bridge, and semiconductor is a heart of electronics. So let's talk about this specific material a little bit more, that how are they going to actually act. So the very first thing we have to see is about the conductors. In their valence shell, they're only going to have 1 electron. So how does it work? This conductors typically only going to have 1 kind of valence electrons on their shell or on their some kind of valence shell, as you can see over here. And because it is a single electron far from the nucleus, the bond is so weak. Right now, it is some kind of so further from the nucleus itself, so it's not going to sense that much of the energy and gravity. It means that if I can find external source or external energy in a form of heat, in the form of voltage, in the form of anything, I can maybe, or not maybe, most probably, I can help him to get out of the atom itself and become a free electron for himself. So the sea of electrons, these electrons easily detach to become the free electrons, as we just mentioned. When voltage is applied, billions of these free electrons drift together, creating the currents. As you guys remember, the very important part, or their very important subject that actually can make current is electron. The proton and neutron are so tight in the nucleus part of the atom, so they can't move. But electrons, they can move easily if you're talking about the conductors and semiconductors. So material, we do have the silver, we do have the copper, we do have the gold, we do have aluminum. Then let's talk about the insulator. As I just mentioned, we do have 8 electrons on the valence shell. That means that everything is so tight. So in insulators, they do have full valence shell of 8 electrons. So this is going to be a state of maximum chemical stability. So it's going to be so hard that at this some point it's impossible for us to make one of those electrons to move from its atom itself. So we do have the resistance. Because of the shell is full, the electrons are tightly bound to the nucleus. There are no empty seats for new electrons to enter. As you can see, everything is full, and no loose electrons to leave. So this results in very high electrical resistance. That's why these materials, or as insulators, they don't allow to current path. So what are the application? We are using that dielectric incapacitors. As you guys remember, we are going to use that in order to increase the capacity of capacitor. We are going to use the wire insulator. So while we do have the copper and other kind of conductive material inside the wire, we do have the insulator outside because we would like to separate them in just in case for the safety if someone touch it or if something kind of short circuit would happen between the real wire itself and the outer environment. And we do have the high voltage insulation itself. Let's talk about the important part. Let's talk about an interesting guy, which is the middle ground or semiconductor. Semiconductor has four electrons at the valence shell. As you can see over here, it's four electrons out of eight just occupied. So this guy is considered as a hero material. Why? Because semiconductors are chemically halfway between the conductor and insulator, between one electron to eight electrons. They have four valence electrons. It's just full half of shell. So what is the characteristic? They are not going to be useful because they conduct well. They don't, and also they are useful because they are going to be conductivity. They're going to have conductivity that can be controlled. Why does it mean? What does it mean by controlled? We are going to talk about it. It means that somehow by doing some kind of mathematical things, we can change the number, we can change the electron at the outer shell, and we can somehow consider them as a conductive, or maybe we can do another thing and we can consider as an insulator. So versatile, by adding impurities, that we call it in the future, doping, or changing the temperature, we can manipulate the silicon to act like a wire or rock. That is the beautiful part of semiconductor that is going to shape the electronics. What can we do in order to have our silicon, at this point, silicon is considered as a semiconductor, to at one point act as a wire and at another point act as a rock? So the primary material that we're going to use is going to be a silicon that most of the time. So let's have a little bit deep dive over here and see that what is going to be the silicon crystal lattice, how we are going to see that, what does it mean for electron, so on and so forth. So here's the thing. Silicon has four valence electrons. It means that in the outer shell layer, it has four electrons. But wants eight to be stable. As we all know, every atom in the universe wants to be stable. So in order to be stable, either it has to receive electrons from another materials in a normal way, or it can share those electrons with their colleagues, with their guy beside them. So what is the solution? The covalent bonding. This is bonding between the atoms, between some kind of specific part of materials, that each silicon atom is going to share its four electrons with four of neighbors. As you can see over here, I do have some kind of one silicon and I do have another silicon. So these two guys are going to share their valence. They're going to share the electrons together, and at that point, they're going to reach to a specific balance condition. What is the result at this point? The result is that each atom effectively is going to seize 8 electrons. It's not necessary to say that the 8 electrons is going to be for itself, but it's going to seize that one. So at this point, let's just consider the middle brand, maybe this guy. As you can see over here, we do have one electron and two electron. This means that one electron is from this silicon and one electron is from this silicon. Then we do have the same scenario for here. One electron is for this guy and one electron for this guy. Same scenario over here. So 4 electrons comes from one silicon and 4 electrons comes from another 4 silicon atoms. So at this point, my guy, which is the middle silicon, can see 8 electrons in some kind of in its bonding. So the important note over here is that at absolute zero some kind of degrees, that we can most of the time when we're talking about degree, we talk about the Kelvin. This lattice is going to be a perfect insulator. It means that this guy is just stable, so it's not going to do anything. It's just hard as a rock. So let's talk about energy band theory because it is kind of important thing. So what was the valence band? As we all know, the valence band was the outer layer. It is the part that where electrons normally reside, bound to the atom. So as we know about that, this is going to be an outer layer. We do have the electrons there, and based on the numbers, we can categorize. What is the conduction band? The conduction band is where the part electrons must jump in order to flow or become electron or free some kind of current. So what should happen for my guys to be at the conduction band based on the specific energy, based on the specific material? We do have the conduction band. Then we do have a forbidden gap is the energy barrier that electrons cannot exist there. They must jump. So this is the part that when we do have the valence band, we are going to give them some energy and they're moving to the conduction band. When we give them enough more energy, they're going to be in the forbidden gap that they cannot exist either. They have to move back to the conduction band and the valence band, or they have to move freely. So semiconductors are going to have the gap small enough that external energy can bridge it. That's a good thing about some kind of semiconductor. So as you can see, we do have the conductors and they do have the conductive band, some conduction band, and they do have the valence band. You see that everything is so fragile. That's why they can move easily without any kind of issue or with just a very small amount of energy. Then we do have the semiconductor that they do have the forbidden gap that it's need only around 1 electron volt, which is going to be the unit measurement for energy. We do have the valence band, then we do have the forbidden gap, then we do have the conduction band. But on another hand, we do have the insulator. They do have the valence band, but the forbidden gap is so high. And it needs so much energy for this guys or each electrons that moves over here to reach to this point, then move to this point, and after that, it can move freely. That's why we can say that insulators are completely immune against any kind of current. So let's talk about the catalyst. Let's talk about the temperature effect, that what is actually happening inside our silicon. So here's the mechanism. The thermal energy is going to do what? Is going to give them energy that vibrates the lattice atoms. With enough heat, the covalent bond is going to break. And valence electrons require enough energy to jump to the forbidden gap. If I do have enough energy, those guys can have the specific electrons do have another energy, do have enough energy, and they can jump to the forbidden gap, which is something somehow we like but still we need more energy to move them some kind of further because just reaching to the forbidden gap is not enough. So the inverse rule about that, some kind of the metal is going to be considered as the conductor. If you increase its temperature, the conductivity is going down due to atomic collisions. So this is about the metal. This is about the conductor. If you heat up, you do have actually more resistance. And then if you have more resistance, electrons can move some kind of harder. That's why it's going to be hard. It's going to be tough to make it as a conductor. It's going to be harder and more challenging if you increase the temperature time by time. Then we do have the semiconductors. If you increase the temperature, the conductivity is going up due to more free carriers. So that is the good part. So what is the impact? The electronic circuits using semiconductors, and they're highly sensitive to temperature and often require thermal compensation. That's why we have to be very careful when we are dealing with semiconductors in specific temperature itself. So let's talk about another concept, intrinsic with extrinsic materials. What does that? Intrinsic means that the pure materials. What is the pure materials? Imagine that you just have silicon. You just sit tight there by itself. All of those specific atoms, they do have the covalence connection and everything is stable. Nothing is happening. Nothing is strange. So we do have the perfect structure. We do have low conductivity, and obviously it's not useful, right? Because what is this difference between the insulator? We're not going to use that. So the pure silicon is going to be academic curiosity. It means that right now is a very good playground for ourselves to do some changes. What does it mean? By changes means that we have to add some impurity in it, or we call it as extrinsic or pure silicon. What does that mean? Imagine that you do have the silicon and you're going to inject some impurity in it. By injecting some impurity, it means that we do have some imposters. So those imposters are actually going to do something for me by changing them or by just giving some energy to them or by some kind of put some boundaries or rules for them. We are going to make imperfection, and it means that high conductivity, and it's going to be useful based on the time that I actually control them. So as you just mentioned, the silicon is going to be of academic curiosity. To make it useful for electronics, we must introduce inquiries to change its electrical properties. So this process, as I just mentioned, is calling that we call it as doping. We will talk more about it actually in next chapters. So far, we learned a couple of important things. First of all, we talked about the valence shell or the number of electrons inside the valence shell is going to decide or is going to show you that how the material is. Is it a conductor? It means that it only has one electrons on the valence shell. Is it a semiconductor? It has four, and if it is an insulator, it has eight. Another thing that we learned was about the band gap, that we do have the no overlap. It means that the free flow sea of electrons we see in the conductor. And when we do have the forbidden gap or that specific orange gap, if you remember, if it's small, it means that it is controllable based on the temperature. It is so sensitive. And if it was large, it means that rigid and we don't have any flow itself. So at this point, guys, we'll talk about a very important part, an introduction section of electronics. We talked about how we can categorize the materials, why we categorize it like that, and so on and so forth. So in the future chapters, on the future part, we are going to touch this some kind of the formula wise. We are going to touch that actually how they are going to act, how they're going to work in detail when we are talking about the semiconductor, what we actually mean by adding the impurity, what kind of material we are trying to make, and so on and so forth. So if you just like this video, I would be more than happy if you share it. Don't forget to put comment for me if you have any question. My name is Mahmoud Kiasari. Have yourself a great day, night, whatever. See you.